Today we will continue our lecture. Okay, today we will continue our lecture. We have going forward to the multiple integrals. So this is the last chapter in our lecture. Okay, so I hope you you know that. So today is June 8th, right? And our final will be it's between this week, right? From 21 June is we have the final week. Maybe later I will let you have a survey to fill out which schedule you prefer. I prefer to be probably 25 on Friday, or if we cannot have any like set of schedule, but maybe Saturday, maybe Saturday, but I will let you know later. Okay. Back to the lecture. As I mentioned previously, last week, we have the introductions of how we are going to approach the multiple integrals. So basically, multiple integrals is if you are approaching an area under curve in calculus 1, in the multiple integrals, we are approaching the volume. Okay, this part of this volume. Okay, and by doing that, actually, I suppose this region R is larger. Okay, and this is basically you can project the surface inside this region. Okay, maybe I will make it larger a little bit so that it will make much sense. Okay, and you can project and mapping all the points from the xy plane to the surface. Okay, so basically that, and you can make out a small rectangular shape out of this region R, and then having the projections from the surface, you can approximately find the volume, right? And this will be your approach. Okay, this should be written as double sum, okay, because you have sum on the x-axis and sum of the y-axis. Okay. You need to add all the rectangular on the side of x and the y, right? And that is this sum. I mean, I try to simplify this sum by making ij. So this means and it should be probably having two numbers, m and n. This means m, and or let me rewrite all this again in the new page so that you can have a good view. So volume will be a limit as m and then n. They both approaching infinity, and you have both two summations. And you also have the coordinate that will make the z as the height, and then you have the delta of the area. And this will be the definitions of the double integral. So because it has two summations, you will have two integrations like that. And let's make the r and make the coordinates and then dA. So this will be the double integral of f over rectangle r. Okay, so you need to be distinguish this meaning from what I define here as a region. So the r in this case is our projections here. Okay, so basically that is the definitions. Okay, and this provide the limit is exists. Okay. There are also some precise definitions, but I think I will skip that because uh, we have 9 sections, like from 15.1 to 15.9. Probably I will skip some parts in between. So I'll just share with you the key and the important or essential integrals for this chapter. Okay. Okay, let's continue a little bit. Okay, if you want to look more closely, oh wait, oh, in this. If you want to look more closely to what we are going to observe, is this is what um, the definition said. Okay, so you have a projection from the surface. So this is part of the surface. This part, okay, it's part of the surface, and we want to project it to onto the our xy plane. Okay, and then we are going to have a rectangular. So we have this area here. Okay, this area, and this is how it looks like when we approximate. And with the amount of m and n, as long as those two going larger and approaching infinity, we will have a very smooth surface. Okay. And let me add also some notes here. If f has both positive and negative value, and it's possible, it's not necessarily always positive, so it's sometimes you can have both values, then the volume is the difference in volumes between R and surface below and above xy plane. So it's basically subtract between those two. And then if the functions is positive or greater equal 0, like in the definitions. So if functions is positive, then volume of this solid and below the surface this will be volume. It's basically what we have right in terms of limit definitions. So this is the volume. And there are, I think if you check your textbook, some example, I will skip that. It's the Riemann sum, but using the double Riemann sum. I will skip that. And also the midpoint rule, basically that is actually the same cases with the calculus 1 Riemann sum, but you just need to have two summations for x and y. But I will skip that for now. Let's just go to the iterated integrals. So how to evaluate and how to observe of the double integral. So suppose you have, well, let me write the iterated integrals. So suppose you have functions and you have the endpoint on all the double integrals, and you have dx dy at the as its differentials. What you are seeing here is basically how to process or how to evaluate is the inside is going to be the first step. Okay, so this is the first step. Okay, and after we got the first step, then we can move on to the second one. Okay, let me show you the example. Maybe here. So let's just evaluate. Okay, now we compute this first. Okay, so it's like a partial derivative, but it's integrals. Okay, so you are seeing the dy at the first step, right? So you need to integrate with respect to y. So what is happening is still write the outside integration 0 and 3, and now you are set up the integral for y. It's the half y squared, right? So you can write, let me write different color. So half, and then x squared, and then y squared. Okay, and this will be replaced by 1 and 2 to be calculated later, and then you still have the x. Okay, you put in 2 and 1 into y, and then you will get 3 over 2 x squared dx. And now you can integrate with respect to x. You will get x cubed over 3. Sorry, over 2. And then plug in the rest of the points, you will get 27 over 2. Okay, now look at the equations at here. Look at this is dy dx. What is happening when we are changing this and changing also this? Okay, so it's become 1, 2, 0, 3, same equations, but it's dx and dy. So same thing, we are going to compute the first integral that are inside. So write this as 1, 2, and then integral with respect to x. So it will be x cubed, and then 0, 3, and then dy. And then you get 27 over 3 y dy. And then you get, it's actually 9y. And then, but let me just write this. All right. So 4 minus 1 is 3, so it's same results as the previous, right? Same results. Okay, so to solve the problem, sometimes you can reverse the order whenever you think the integrations will be much more easier. Okay. That is the definitions on the, we call the definitions in theorem of Fubini or Fubini theorem. So if functions is continuous on rectangle of R, which is on XY plane, and you have this all this endpoint, and then you have and it will be the same as you flip the order. Okay. I think the proof of this theorem, I don't think I need to write it as of now, probably later. But at least from here, you get the point of the theorem, okay, that you can easily reverse the order. Okay. The next thing is, so actually, I want to try to summarize as I can the first part of the chapter 15, because it's mostly introductions, so that you can skip some part of the textbook. Let me write some property that you might need on multiple integrals. Of course, if C is constant, you can factorize this C out of the double integrals. If you have double integrals and you want to plus or you want to minus with the other double integral. Oh, wait, I think this should be inside first, and then I will move to the outside. So both of these two functions inside one double integral, and you can separate them. Oh, okay. Forget the A, R. So you can separate. I think this is already in common with the calculus 1, so I will just skip that. I think number 3 is important for the multiple integrals. So the next thing, aside from separating, if there's two functions, you can separate two functions. You can also separate the R. So you can separate the rectangle. So it's still the same functions, but the endpoint you can separate, become two set of points in which you have R is R1 plus R2. And then if you have a multiplication of two functions inside, you can also take this as integrations of gx, dx, and then integration of cd of h of y, dy. You can also separate the double integral and then becomes the single integral. Okay. So I think this property are quite important, especially the number 3 and number 4. Okay, the last part on the 15.1 is about the average value. Okay, if you have any questions, you can just type in on the chat box if you need to ask. Okay, the average value. If you remember, on calculus 1, you have this average value. But now, the average value, because now f is a function of x and y, now you have the area of R. And if the function is positive, the equations we can write, so multiply with the average will be double integral. Okay, I think that will be the end of the 15.1. I think for today, I can make up until 15.2 or 3, maybe just a little bit 15.3, but probably focus more on 15.2. So this is 15.1. So this is 15.1 and here. Okay. So I'm skipping a lot of things in 15.1, including the Riemann sum. I'm skipping that one. Okay, now 15.2. This is called the double integral over general regions, which I actually already explained before. So let me just rephrase what is the importance or how to measure the double integral. Okay, imagine you have a surface maybe here. Before, what you are doing is you are projecting to the xy plane and making the projections, right? And then making the rectangle. Okay. What we are going now, we are having some region that is larger than the projections, and it's not a rectangle. But actually, this is actually, if you see the graph, this is actually the same thing as we have done before, right? You have the, if I make it into 2 dimensions, you have, first is if your if this is your, or maybe let me make more because it's too obvious that this is rectangle, right? Well, let me change the graph. And let's change the surface. It's too obvious. Let's change the surface like that. And what we are going to do is we project this into here, and we will put a box now. So if you, I don't think I need this right now. So this is, let's say this is D, and this is R. So suppose D is a bounded region. Which means that D can be enclosed in a rectangular region R. So it can be closed in rectangular region R. And in order to integrate, let's say this is having a functions of f. Okay. Instead, just looking at this f, okay, and then how to observe in more a clearer way, we need to develop a new functions. Let's say the big F. This functions is describing the small f and also the region R. So by making this into 2 definitions, that is the big F, it's the same as the small f if all the points x, y is in the bounded sets, right? And we can make a definition that the big F here is equal 0 if all the points is in R, but outside of the, or not in the. Okay, so I hope you get what is the point from these definitions. So based on these definitions, you can have or you can observe the double integrals from any general regions. Basically, not necessarily to be rectangular. Okay, so you can apply it for any different regions. And basically, we have 2 types. Okay, 2 types of R. Okay, because we have dx dy or dy dx. So the terms or the graph or the types that we are going to evaluate will be dependent on this x and y. So for example, let's say this is type 1. I think in your textbook, they mention type 1 and then explain something, and then type 2. I will just giving you what is the summary, okay? And you can look up and try some exercise. So type 1 is basically, let's say this is, we have two curves here. The first one is, let's say it's a function of g, let's say g1 and x, function of x. And then let's say the second curve is function of g. Remember in your integral in the calculus 1, the area here, right, is g2 minus g1, right? The order, okay? So this will be the same or similar case that you need to also consider. If this is x equal a, and then this is x equal b, then the integrations, let me write the general integrations. This will be a, b, and then the second integration here, the inside integration is from g1x until g2x, and then f x y, and then dy dx. So the first type is if you have functions of x, okay, function of x. So you have y equals something functions of x, okay? And in the exercise, it depends which two types that you, if you can solve by both, it depends on you, which whatever method you want to achieve. But sometimes you can tell from the questions that you need to have the function of x or functions of y. Okay, the second one is function of y. So we will have, let me draw maybe here. We will have this 2 point and 2 boundary, which is the y, sorry. Let's say it's C and D. And then you have, I'm just randomly drawing the curve there. So this will be x. And this will be h1. So functions, so h is the functions, okay? Function of y. And we have the formulations. And always start to write the integrations and set up the constant as the outside integral, okay? And then dx, dy. Okay, so this is type 2. So type 2, we have functions of y, and type 1, functions of x, okay? And then the region R is described as you can see on the graph. The type 1 is the x is from A to B, and the y is from G1 to G2. And for type 2, the y is from C to D and x is from H1 to H2. Okay. There are some examples on the textbook as well, but let me just give you the examples about the type 1 and type 2 and how to use it on the more practical terms. Okay, evaluate this, and D is bounded by these two curves. Okay. Now the important thing on the double integral now, it's not drawing the volume as it is, but rather we need to draw the boundary, the D, okay, and in this case, or R. Maybe sometimes they are using R, sometimes D. Okay. So basically, first, it's important to have a drawing. For most of the cases, it will help you to think. Okay, let's say that is maybe the y equal to x squared. And the other one may be around here. It's not really too proportional, but I think it can just illustrate what we want to set up. Okay. So this will be the area that we want to surf. The area that will bound the surface. Okay. So where is the surface? The surface is on above this area, right? Now, the idea of integration is aside drawing, you need to be able to tell the intersections from this. Usually in the double integral, you need to be telling how to find the intersections, how to find the set of points that is going to be evaluated. Okay. So now you have these two, right? So we can evaluate this and then finding the intersection in which you can tell that this is having on -1 and 1. So this will be 1 and this will be so maybe here -1, this is 1. So 1 and 2, right? So maybe, okay, maybe right here if you want, but I don't think it's really necessary as long as you get the x is equal 1. And then basically you can measure the integral. So x plus 2y, and then x is from -1 to 1, the constant. And then the second integration will be the functions. Okay, I hope you can follow all these steps. Okay, and then basically what you are going to do is first solving the inside integrations. So write down the outside still the same. So write down the integrations from here. Integration with respect to y, it's xy plus y squared. And then we have the endpoints. We plug in the endpoints, and you will get it's thing takes really long to write. 1 plus x squared plus or minus, or maybe I will plus all. Okay, plus all. So plus x 2x squared. Okay. Maybe plus all. Sorry. And then minus the other second terms. X all with dx. Okay. And then integrate this, evaluate, integrate, and then plug in the value. You will get this will be around 32/15. Okay. But what the point is, on these multiple integrals, sometimes the calculation is important, but the concept, okay, what I want you to understand is basically the concept of these two double integrals. How to define this in the double integral. Okay, that's the most important thing. I think calculation, all of you can calculate, all of you can do the integrations. Okay, but the how to set up the integrals is the most important. Okay. Okay. Let's give you another maybe some notes first. Okay, so you can actually, because you know that the volume is usually used for to know that this is the double integral, but actually you can compute the area evaluate the area using double integral. You can also do that. Okay. How? If you remember the illustrations that we did, we have this surface and we have this region projecting blah blah blah, right? If z is 1, then actually, let's say usually you have area multiplied by h, but if h is 1, so the volume is the same as area. So basically, if in this case, you can take the double integral and dA, and this will be your area of R. This way you can also compute the area. Okay. Okay. Maybe one more example for the double integral. One more example. Find volume of solid that lies under Okay, we have this questions now. Okay, first we can draw. Think we can draw like that, and maybe this is 1 1, then I can draw the line. Let me draw the line first. Okay, and the second curve, we have y squared, so it's supposed to be parabola to the y-axis as the center of symmetry. Maybe around here. Maybe around. Yeah, actually, I'm just randomly drawing the parabola. But let me make much more sense. Maybe there. Okay. I think that should be good enough. So we need to find the area inside, right? As our region D. Okay. So first, we need to find this intersection here and here, right? If we look at first, the giveaway is this functions y squared, right? To be able to make the connection between these two equations, you need to think which one is preferable, right? So instead of writing in terms of y, we can solve it in terms of x, right? So x is y plus 1, 2x is y squared minus 6, and we can substitute both of this. Or we can make it equal and we solve this equations. From here, we get 2 points, exactly 2 points. And that's the point that we want to observe, right? This -2 and this is 4, right? Okay. Now this is y, so of course we get the volume will be, this is from -2 to 4, and then this is from the x, the equation of x. So y squared minus 6 divided by 2 up until y plus 1. Okay, and the equation of the function is z equal xy, and then dx dy. Okay. So you can start by taking this integral first. Okay, first step. But I think I will skip the process. You can do that by yourself. But this is already all the concept of the multiple integrals already already in here. Okay. Okay. So first, the important point here is you need to draw the region. So you need to understand which one the curve is. Okay, like for example, this curve here, because it says that which one is the top equations, it's the blue one, right? If you are rotating the curve, like integrations, you have top minus below or right minus left. So the blue one minus the left, the green one, right? So of course the draw region will be essentials. The second part is you can reverse the order if necessary and use the Fubini theorem to reverse the order. Okay. By the way, if you check this volume, it should be 36 you compute. Okay. Any questions? Any questions from all these examples? Okay. Let me go to the next page. Let me put into the 15.3, and I will just skip some example on 15.2. I think I can go back if I need it, but I think I can go forward. There is some theorem, but I don't think that's important for now. I think we can go just go to the double integrals in polar coordinates. So double integrals in polar coordinate. Okay, remember you have the circle that is the foundation, the basis foundation of the polar, and all the point of x and y that you can convert into r cosine theta and r sine theta on polar. Okay, and of course this is based on this is r, this is theta. Okay, so this will be the polar. Okay, how to convert is through this tree. Okay, that's the essential parts. Now move on to the integration part. This is quite let me just draw first some visuals for you. So let's say this is randomly surfaced there. And let's make the xy plane in terms of polar. Okay. And let's take the first theta as alpha, and the last theta here beta. So we will observe from alpha to beta. Okay. Let's say this is z is, let's make it into r theta. And from the xy that we have learned before, it was supposed to be, the Riemann supposed to be x and y, but because x and y can be converted into the polar, we can convert the x with the r, and then dy is sine and it will be with delta A. If you want to look in more in depth, let's use this one here. I think this should be clear enough. Okay. So if you look here, we have a region R that is bounded by theta and R. Okay. And if you take some cuts, okay, from all this R, we will have this similar to what we have done in rectangle, right? But now we have, and this is called the sector, right? So the sector, area of sector. Remember that the area of sector is half r squared theta. We have done in the chapter 10, right? And how to find this, the delta A here is through the large sector minus the small sector. I think we can try to write some value. So from here, let's take the Ri, so half. Let's say this is R1, R2, and let's take take some random R in between A and B. So this will be Ri, or I may write here, Ri is the center of the polar rectangle. So if you see here, this rectangle here, the center is Ri and theta. Okay, so let me write here, the Ri is actually and the theta is half. Okay, this is to set up the R and theta as the center of the rectangle. So we have, it's like a midpoint rule, right? Like a midpoint rule. So this is, we have R1, Ri, sorry, and then delta theta minus so we have the difference on this R. And we can factorize the quadratic. And let's define these terms here as this, right? So this is Ri, and then this will be the delta. So all in all, this will be Ri with asterisk and delta R and delta theta. Okay, and then back to here, we can write down and change the delta A. So we will have this will be r, delta r, and delta theta. And if we write this f into a functions g that is ri and theta j, we can set up a more settled. Okay, this is the last part. I will stop here. Let me just write the last one here. Okay, or you can write down in terms of g r theta dr d theta. A, B. Okay, so that will be the last part that I can explain to you for the polar. Later, I will show you the examples on how using this polar. Basically, we're just going to write up the functions, and then it's always dr d theta. Okay, most of the case. And the rest is depends on what questions they have. And of course, because it's polar, you need also to check your chapter 10, right? Like maybe you have this, or maybe with the loop, or maybe this, all the polar that can have in shape. Okay. Okay. Actually, we will have a quiz now. You can check the Google Classroom. I just posted. I'm scheduling the announcement for today. Please just use the link, and then don't forget to write your name, student ID, and yeah, basically you don't need to write the paper calculations. You can read your notes if you want, and just please take a look first for the forms. Okay. Okay, so the time is actually let me check the time. I'll write 20 minutes, but I can give you 25. Okay. So it start from now until 2:55. Okay. Okay. Have you checked? Okay. If you have any difficulty for the link, let me know. Okay.